Good morning. Today we are going to discuss the topic the parallel plate capacitor. So we have seen the capacitor, the behavior of capacitance and what is capacitance and all in the previous sessions. Now we are going to discuss the parallel plate capacitor. What is a parallel plate capacitor? A parallel plate capacitor consists of two large plain parallel sheets or conducting plates separated by a small distance d. And first we consider that the intervening region between these two plates is vacuum. And let A be the area of two parallel plate conducting surfaces. Both have the same area. And D is the separation between them as I said before. And these two plates acquire the positive charges plus Q at the plate 1 and minus Q at the plate 2. So also these two plates have a surface charge density plus sigma at the plate 1 and negative sigma at the plate 2, because both they are positively and negatively charged. So how a parallel plate is charged and how does it acquire this positive and negative charges? We have seen that when this one plate is grounded, then uncharged plate brought nearby a charged plate and then grounded, then it will acquire an electric field will be produced in between these two plates and that act as a capacitor. So the surface charge densities are plus sigma and negative minus sigma. And these two conducting places, since they have both the same area, and they will act as a infinite plane sheet of uniform surface charge density. The surface charge density can define as sigma is equal to Q divided by A. So now we are going to discuss about the electric field in the outside region of the two plates, and this is taken as region 1, this is taken as region 2. And how does it the electric field? So since both they have the different opposite charges in these two regions, so what will happen to the electric field? The electric field produced there on the basis of the charge density will be cancel each other. So we can say that the electric field E is equal to sigma divided by 2 epsilon 0. And the net electric field will be the difference between this, the electric field or the surface charge density produced by this 2, then that is minus sigma divided by 2 epsilon 0, that is equal to 0. And it is same in the outer region of the second plate, that is here. Here also we will have the same, that is E is equal to sigma divided by 2 epsilon 0 minus sigma divided by 2 epsilon 0 is equal to 0. And then what happened to the region? The inner region between these two plates 1 and 2. And so the electric field produced by the net electric field in the inner region will be the sum of these charge densities of these two plates, that is equal to E is equal to sigma divided by 2 epsilon 0 plus sigma divided by 2 epsilon 0, that is equal to 2 sigma divided by 2 epsilon 0, then 2 will be cancelled. Then what will be there? Sigma divided by epsilon 0 will be the net surface charge density, or the value for magnitude of the net electric field in inner region of the two plates. From this value we can get the value of E is equal to Q divided by epsilon 0 into A. What will be the direction of the electric field? The direction of the electric field will be from positive charge to the negative charge, and that will be the direction of the electric field. And what will be the potential difference between these two plates 1 and 2? The potential difference can be written as V is equal to V. If V is the potential difference, that is the electric field produced by the two plates times the distance separated by them. And the value of E already we know that is Q divided by epsilon 0 into A into D. So we can write as 1 by epsilon 0 into Q divided by A into D. Therefore, the capacitance of these two plates, and we already know that the capacitance C is equal to, so if we substitute the value of V in this equation, so what we will get? Q divided by V is equal to 1 by epsilon 0 into Q into D divided by A. So Q and Q will be cancelled. What we will get there? We will get epsilon 0 into A divided by D. From this equation, if we substitute the values of, and where epsilon 0 is the electrical permittivity of the medium vacuum, and A is the area of the conductors, and D is the distance separated by these two conductors. So if we observe this equation keenly, and what makes the capacitance of a parallel plate conductor, what factors are affected by the capacitance of a parallel plate conductor? So here the electrical permittivity, as much as the value of electrical permittivity is increasing, so what will happen to the capacitance? The capacitance of the conductor will also increase, and also is the area of the conductors. So the area of the conductor is also directly proportional to the capacitance of the parallel plate capacitor. So the electrical permittivity of medium, here we have taken the medium is vacuum. As much as the electrical permittivity increases, then the capacitance also can be increased, and the area also, as the area increases, the capacitance of the parallel plate conductors also can increase. And what happened to the distance separated by them? If the distance separated by them is increasing, so what will happen to the capacitance? Definitely the capacitance of the parallel plate conductor will decrease. So that means if the distance is close, so then the capacitance is maximum. And if we substitute the values of the electrical permittivity of the medium vacuum, and which is 8.85 into 10 raised to minus 12 into, and the area is taken as meter square divided by the distance separated by them. So when we simplify this value, we get as 8.85 into 10 raised to minus 9 farad will be the capacitance of this